Okay, let's talk action-reaction pairs. It occurs to me there have been some questions that have come up about that, and maybe that's something we haven't talked about enough. I think this is a good way to help you get a grip on this a little bit. Let's think about a situation here where we've got a, okay, this is what we did last period, and this worked okay. We've got a weight, we'll say, call it a bucket. That's hanging from a rope, okay? And let's look at the force. Let's say it's hanging at rest from a rope, okay? What are the forces acting on the bucket? Gravity, okay? So let's draw these in then. We've got a gravity force that's acting down. Okay. What's causing that gravity force? What is? Yeah, the Earth is, right? There wouldn't be a gravitational force if this were happening in outer space. Because this is happening near the surface of the Earth, there is a gravitational force because the Earth is pulling on the bucket, right? Okay, so separate from this bucket down here, we've got the Earth, and there is a force of mg pulling up on it also, though, right? Because we always know that forces occur in pairs, action-reaction pairs. Forces can never happen in isolation. They always have to happen between objects, okay? Between objects with mass. Okay? So, bucket pulls on Earth, Earth pulls on bucket, okay? If I could do the same thing with a pencil. If this pencil has some weight in my hand, how come? Because gravity's pushing down on it, right? What's pulling on the pen? Well, I mean, what's not really, my hand is, okay, I'm holding it, but when I let go, it's going to accelerate, right? How come? Because gravity's acting on it, and that's the Earth pulling on the pen. Okay, close your eyes and just really just see if you can feel this. Ready? Just really pay close attention. Okay, did you feel the Earth rush up to meet the pen? It did. It honestly did. Had to. But it probably wasn't noticeable. Okay. Okay, well, I mean, not just we're used to it. It does. Every time you jump up in the air, the Earth comes up to meet you. But the reason the Earth didn't noticeably rush up to meet the pen is because the mass of this pen is something like, I don't know, 10 grams or something. I mean, really tiny. And the mass of the Earth is 5.98 times 10 to the...
More than 10 grams.
Yeah, a lot more. Right. It's big, right? The Earth has a tremendous amount of mass, and so it's not affected very much, right? Okay, but when we look for, one of the things we'll probably talk about that'd be really fun to talk about would be the search for extrasolar planets that might sustain life, because that's something that we're starting to be able to do a little bit. There are several different techniques that astronomers can use to hunt for extrasolar planets. One of them is they look for a wobble of the star. Now, why would a star wobble?
Gravity.
What do you mean gravity?
It's being pulled on by a force of acting on it, causing it.
Okay, what force might be acting on, if we're looking for stars that have planets, what force might be acting on the star? The planet, aha. So if we were to look at the system of a star and a planet, as the planet revolves around the star, well, that's really not accurate. The planet does revolve around the star, but really what's going on when the planet moves around the star is that the planet and the star both move about a common point, somewhere between their centers of mass. Okay? The star has so much more mass than the planet that the center of gravity of that system is much, much closer to the center of the star. In fact, it's actually inside the star, right? Because the star has so much more mass than the planet does. But as the planet moves around, the star is going to wobble just a little bit with it, okay? And as the planet moves around the star, we can see that wobble because stars, the light that that emanates from a star is very predictable. It comes from, why does it, what are the constituents of a star? What's 99.99999% of a star made of? You know what element? Hydrogen, yeah. Then there's some helium in there too, but what you're really looking at is you're looking at the spectral lines of hydrogen when you look at a star. If you were to use a spectrograph and analyze the light, there's going to be, the light is going to follow the specific fingerprint of a hydrogen atoms, of the light that emanates from a stimulated hydrogen atom, okay? But what happens then when the star wobbles towards us, that fingerprint gets Doppler shifted a little bit towards the blue, so it's going to, if you look at a spectroscope, and we'll talk about this much later in the year, just a little bit, you look at the frequency of light determines the color, right? So if you look at the fingerprint of like the intensity of light as a function of frequency, it's pretty flat, and then there's going to be some little spikes in there that have to do with hydrogen, right? With the frequencies of light that are emitted by hydrogen. And so this is towards the blue end, and this is towards the red end. And when wave emitting objects move towards an observer, what happens is the frequency gets shifted to a higher frequency. So objects that are coming towards us, their light would be blue shifted very slightly. We have such spectacularly accurate spectrometers that we can measure, you know, these very, very tiny shifts in the star, as small as, you know, a fraction of a meter per second. That's it. We can measure that by just looking at the light from the star. And so we see that the light from the star gets blue shifted, and then a little bit later it gets red shifted. What's that telling us? The star is wobbling a little bit, okay? And so why do I bring this up? Because that's a great example of an action-reaction pair, right? You can't feel the Earth rushing up to meet this pin, but if a planet's revolving around a sun, there actually is a noticeable effect there because the planet's pretty massive too. And the star does wobble just a little bit, okay? Does that make sense? Okay, so going back to our picture here, this is what we would say constitutes an action-reaction pair, right? Object A acts on object B, and therefore object B acts on object A. You fill in the blanks for A and B. In this case, it's bucket and earth. Earth acts on bucket, earth pulls on bucket, so bucket pulls on earth with equal magnitudes. It's just that the magnitude has a much more obvious impact on the bucket because its mass is so small that it has a pretty large acceleration. The Earth's mass is so huge that the acceleration is vanishingly small when I drop the pin, right? Okay. Questions on that? Does that make sense? Okay, what about this? Well, here we've got this other force acting, a tension force, right? So the tension force, the rope is exerting this tension force on the bucket, and it's pulling upward, right? Well, let's fill in the rest of the picture here. Turns out there is let's say a helicopter is hovering over the ground, and the helicopter is supporting the bucket, right? So then if here's my helicopter up here, crappy helicopter, but you get the idea, right? There's my crappy helicopter. But if it's tied to the helicopter, then what's the action-reaction pair that's occurring between the bucket and the helicopter? Helicopter pulls on bucket, so bucket pulls on helicopter, right? So there's also a force acting downward on the helicopter, right? And those are equal and opposite, they always are. So here's an action-reaction pair, and here's an action-reaction pair. But notice that only one force from each of those pairs is actually acting on the bucket. Okay? Does this force I'm pointing to right here, the upward force on the bucket and the downward force on the bucket, do they constitute an action-reaction pair? Seems like they should, but they don't. And here's why they don't. How many objects are being acted on by this force and this force? One. And action-reaction force pairs always act between two objects, right? Does that make sense? Okay. All right, so,
But they would still have to be like equal and opposite since the bucket is staying in one place.
okay, good, but now here's how we're gonna tweak this. Let's say that the helicopter turns its engines on a little bit, and it's gonna pull up more strongly on the bucket, right? What does that mean the bucket does to the helicopter? Pulls more strongly, because what's gonna happen to the tension in the rope when the helicopter starts to accelerate upward? It's gonna increase, isn't it? Well, that tension is applying force to both the bucket and the helicopter equally, agreed? Okay, so if we do that, that's going to extend both of these vectors a little bit. Okay, and now, Alexis, now, there wasn't previously a net force acting on the bucket, but now there is, isn't there? Now, if we look at the net force, what's gonna happen to the bucket?
Go up.
It's gonna accelerate upward, isn't it? Force pairs, Newton's third law tells us that for every force, there's an equal and opposite reaction force, right? So force pairs also always have to be the same in magnitude. So therefore, these two cannot be an action-reaction force pair because this one could be bigger than this one and we'd have an imbalanced force, right? Which is fine. It just means there's a net force acting on the bucket, right? Make sense? Okay, so what are the forces acting on this mass I'm holding in my hand? Gravity's pushing it down, and my hand's pushing it up. Okay, don't answer right away. Whatever you think about this. Do those forces constitute an action-reaction force pair? Okay, let's vote. How many people say no, they do not? Okay, how many people say yes, they do? Okay. The answer is no, they don't. And how come? Okay, because both the forces act on a single object. They act on the weight. Agreed? Okay, now let's look at all of the action-reaction force pairs acting in this system, okay, that involve the weight. Somebody tell me what is one action-reaction force pair that the weight is involved in? Okay, good. So Earth pulls on weight, so therefore weight pulls on Earth. There's one action-reaction pair, right? Question? Or you want the other one? What's the other one?
The weight pushes, like the hand pushes on the weight, so the weight pushes on the hand.
Right, and it does because I can feel it. I can feel it's pushing on my hand. Okay? Does that make sense? Now, are we interested in both of those? Not really. In the context of this problem, we don't really care that the Earth is being acted on or that my hand is being acted on. We're really interested in just maybe the weight, right? Just like in this picture right here, we probably didn't care about the fact that the Earth was a part of this action-reaction pair and the helicopter. You didn't even know there was a helicopter, right? So I told you. So really all we cared about was that part right there was one force from each action-reaction pair. They still existed, right? Okay, what now? See if we can reconcile this. Because this all kind of, it just takes a while to build this mental picture and really, get some intuition about this. If I push up, so gravity's pushing down with, let's just say 9.8, let's say 10 newtons. This is how much this weighs, let's say, it's round. Let's say I push up with 15 newtons. What's the mass gonna do? It's going to accelerate upward, right? Okay. Does that seem possible though? An action-reaction. How do you reconcile that with the action-reaction pairs? If I'm pushing up with 15 newtons and the weight is only 10 newtons, in a way that makes sense, doesn't it, right? Because there must be a net force of 5 newtons up, so it's going to accelerate a little bit, right? Okay, explain. What's the force acting on my hand then? I'm accelerating it upward. It's greater, isn't it? Well, in fact, what is it going to be? To what? The force I'm applying to the mass, right? I said I'm applying a force of 15 newtons. So doesn't that mean that there must be a 15 newton force being applied to my hand also? Does that seem weird? A little bit? That's right. It's true too. And you can prove this to yourself. If you're holding a rock, let's say we're doing this. Okay, let's say I'm holding a bag of, I don't know, something like let's say I've got a little baggie full of sand. and underneath that baggie of sand, I've got an egg. I'm holding it in my hand, right? Would you agree that if I were to go like that real fast, I could break the egg? Couldn't I? How come? Okay, because I'm going to be increasing the force acting between my hand and the bag, right? And the egg's in between. Does that make sense? So the egg really is the conduit. The force acting between the egg and my hand would increase, wouldn't it? Does that make sense? Okay. I can do that, right? Whatever the force I apply to the egg, it's going to apply an exactly opposite and equal in magnitude force to my hand, right? Okay. Did the weight of the object change? No, it stayed the same, right? The weight is 10 newtons. This thing is pulling on the earth with a force of 10 newtons, and the earth pulls on it with a force of 10 newtons. It's because I use my muscles and push this thing upward that I increase the magnitude of the action-reaction pair between my hand and the weight. Make sense? Okay, how about this one? Let's say that I am accelerating, I'm driving my car, and I step on the gas and I accelerate in that direction. Okay, what are the forces acting? What's the important force acting on the car there? Why do I move forward? Okay, I push on the gas pedal. That's not what's moving me forward, though. That might cause what moves me forward. But what moves me forward? The engine. Okay. Yes, indirectly. But that's not the answer I'm looking for. And I can. What is it? The friction. Okay, we could say it's the friction that pushes me forward, right? Okay. What object is pushing me forward? Because the friction is the kind of force, but forces always act between objects, right? So what's the object that's pushing me forward? We've always in the past been okay with just saying, okay, if we're drawing a free body diagram, the friction is pushing me in that direction, right? And so, or we might call it the driving force or whatever. But now I'm asking a different kind of question. I want to know, okay, what's the object? I mean, something has to be pushing on the car for the car to move forward. Sure, we could call the force friction, or we could call it a driving force, but forces always act in pairs between two different things, right? The car and what? The road maybe, right? Does that make sense? So the reason the car moves forward is actually because the car pushes on the road, right? What does the road do in return? Pushes on the car, right? Here's the proof. What if the blacktop was covered in a sheen of ice? Why can't you go forward very fast? Because you can't push on the ground very hard, right? When I try to push on the ground, there's very little friction for me to apply that force to the ground, right? And so the ground can't push back on me very hard. Make sense? Okay. When you drive forward, if you accelerate forward, the ground is attached to the earth, and so what's actually happening to the earth a little bit when I accelerate my car in that direction? Yeah, it's going to roll back a little bit in that direction, right? Very small amount because the earth is very massive and my car is not. You get the idea? Okay. All right. Good. Let's go through. And this was kind of fun. We did this last period. This was good discussion. Let's go through the review book assignment. And I want you to make each of these each part of each problem worth 2 points. 1 point for attempting it, 2 points for getting it right. Okay, so this is the one on page, page 145. And I'm mostly just interested in.
Can you talk about the tennis ball, like the terminal velocity or whatever?
Yeah, sure.
I didn't get that.
Okay, is that on the problem on here that talks about the tennis ball? Yeah, absolutely. That's a good one. Yeah.
Are we turning these in?
No, I'll just get scores.
Okay, so I put it on another.
That's fine. You just grade it and I'll get scores from you, today if we have time, otherwise we'll get it tomorrow. Okay, so the first one was number 10. If you're in a car that is struck from behind, you can receive a serious neck injury called whiplash. Now, the first part is using Newton's laws of motion would explain why that happens. So here I am, I'll be the crash test dummy here, in my car, sitting at a stoplight, and some bozo runs into my car from behind. Well, what happens to me?
The car goes forward.
Okay, right, there's a action-reaction force pair between my car and his car, Bozo's car, right? And so my car gets pushed forward, my seat is the rigid part of my car, and so therefore my seat pushes on me, right? But it pushes on my back. So my back gets pushed forward. How come, what does my head want to do?
Stay where it was.
Oh, and you're right, it wants to stay put. How come? Which of Newton's laws probably? Yeah, Newton's first law, law of inertia explains that. Now you could, if you wanted to explain this using any of his laws, you really could, that'd be fine. But to me, the one that really sticks out here, the one that really explains this well is the law of inertia, right? Because my head has some mass, objects with mass, a force must be provided to accelerate them, right? Objects at rest tend to stay at rest, objects in motion tend to stay in motion, unless acted on by an external force. Well, the seat provides the external force for my body, but my head has to be accelerated by my neck, right? And that's not, your human neck isn't that strong, and so your head goes flying backwards, right? And it causes problems. So what's the solution? Headrest, yeah, that's all it takes is a headrest. Old cars didn't used to have them, modern new cars, sometimes if you notice, like the newer the car, the more annoying the headrest is. Like they kind of push you, you can't just relax in them sort of when you're driving. But there's a reason for that, it's a safety feature, because if that's in contact with your head, then when you get hit from behind, your head gets pushed with the rest of your body, and so your head, your neck doesn't go flying back. Right? Does that make sense? Okay? All right. Number 12. If you find a pendulum clock, so like a grandfather clock, running slightly fast, how could you adjust it to have it keep better time? What would you do? Sean, what would you do to that clock? What would you do to the pendulum? If it's running fast, that must mean that the pendulum, the period is too short, right? Because it's swinging back and forth too fast. So would you make it longer or shorter if you want to swing slower?
I want to slow it down.
If you want to slow it down so the period gets bigger, make it longer. That's it, right. You just extend the pendulum a little bit, you lengthen the pendulum a little bit, and it's gonna make the period longer so it slows it down. Very good. Okay. Number 14, I don't think I originally assigned 14. I think I slipped that one in on the Moodle assignment, so we won't grade this one. This is just for discussion. What's the meaning of a coefficient of friction that is greater than 1? Okay, now think about the way friction works, right? If we're got a flat surface, got an object at rest on the surface, if I'm going to apply a pushing force to this, right, to try to get it moving, what resists me? Well, if I'm going to push the box in that direction, what's resisting me? Friction, right? Static friction in this case, if it's not moving. Okay. Well, the other force, this force is acting on the box vertically or what? Gravity down. And yeah, and what do we call that? Normal force. Normal force up. Okay. And so if I'm pushing horizontally, would you agree that these two have to be balanced? Right? So the normal force is equal in magnitude to gravity, right? Well, what's our friction equation? Frictional force always equals, with our model that we're using, always equals what? How do we calculate friction? Why is it that if I push a crate on ice, it's going to move more easily than if it's on like a rubber mat? What about?
Unless like surface friction or.
Okay,
like,
yeah, but so where does that come in the equation?
Was static or kinetic friction.
Well, either way, no, it could be either one, honestly. But there's something in there that there's a part of that equation that's going to be different for ice. than it is for a rubber match.
Coefficient.
Coefficient, yeah, okay. Right, so friction equals
Guess what we're talking about.
the frictional coefficient times normal force, right? But in our case, because we're pushing horizontally, that's the same thing as saying friction equals the coefficient times the weight, right? Okay. So what if the object has a weight of 100 newtons and the coefficient of friction is 0.5? What's going to be the frictional force?
Wait, what'd you say?
So if the coefficient is 0.5 and the weight is 100 newtons, it's going to be 50, isn't it? Okay. So the frictional force is going to be 50 newtons, the weight is 100 newtons. So it's a little bit easier, half as easy, to slide the thing as it is to pick it up, right? What if the coefficient of friction is 0.1?
It's the same.
Then what's going to be the frictional force? 100 times 0.1 would be
Oh,
10.
0.1.
Wow. So that's a slippery surface then, right? So it's easy to slide something on a slippery surface. I only have to apply 10 newtons of force to move a 100 Newton object to slide it along the ground, right? Okay. So really what this is doing is it's comparing weight to sliding force, right? Does that make sense? And the weight is just, I mean, that's the amount of force that would be required to lift the thing up directly, right? So it's much easier to slide the object than it is to lift it up directly in those cases. Agreed? What if we had a coefficient of friction of 2? Yeah, I'd have to apply 200 newtons of force to slide the 100 Newton object. Is it probably going to make sense to slide it in that case? What would you do instead? Let's pick it up and move it, right? That make sense? So how would we interpret this then? What is the meaning of a coefficient of friction that is greater than 1? Yeah. Yeah, it's actually right. The frictional force in that case is actually greater than the weight. Okay? That's not normal. It does happen. In the book, I guess they talk about a situation with like the dragsters. Did you see that? Talk about dragsters. Where is that? Somebody brought it up last period. Where is that? What page? What is it? 131. Oh, right here. Yeah. Coefficients as large as 5.0 are experienced in drag race. That's kind of interesting. Think about it. Is that good or bad for a drag racer to have a high coefficient of friction? If you want to win the drag race, is that good or bad? It's good. It's good. How come? So yeah, when you're trying to take off, what's your goal with any drag race, or with a dragster or a regular car? You're trying to apply as much force as you can from the car to what? The ground. So the ground can apply that force back to you, right? So the higher the coefficient of friction, the more force you can apply to the ground, which means the more force it applies to you to accelerate you forward, right? So a 1,000, well, let's say more than that, say a 10,000 Newton, well, what would a dragster weigh? 2,000 pounds? Say a 2,000 pound dragster then, with a coefficient of friction of 5, would be able to apply how much force to the ground? 10,000 pounds, right? And so the ground's going to apply 10,000 pounds of force back to the dragster to zoom it down the road.
How do they make that?
How do they do that? Yeah, that seems kind of tricky. How do they do that? Well, do you notice? And I'm not a big aficionado of dragsters by any means, but I have seen, everyone's seen on TV a dragster. What do the dragsters always do before they take off? They rev the engine. They do something else. They spin their tires, right? They spin their tires real fast and they start smoking. Why do you think they do that? Well, maybe that too, but there's actually a real physics explanation for why they do that. What do you think that does to the tire? Heats it up. Yeah, it melts it. It heats the rubber up to the point where it actually becomes gooey, and so it sticks to the road. And so when they want to take off, do they want to skid when they take off? Not really. What the dragsters want to do, they want to heat it up, and then they want to threshold accelerate where they're not going to start spinning, but they'll use that extra static frictional force to push them forward. So when they take off, you notice they try not to just spin their tires as fast as they can. They actually try to keep the tire sort of in contact with the ground. It's hard to do, but that's the idea, right? That make sense? Okay. All right, what else we got here? 15, right? Using the model of friction described in this book, would the friction between the tire and the road be increased by a wide rather than a narrow tire? Okay, so there's our frictional model. What do you think? Does that seem to depend anywhere on the surface area of the tire? Is there any part of that equation up there? The only parts of that equation are normal force and coefficient, right? If I have a wide tire compared to a narrow tire, is that going to change the amount of force acting on the tire?
But if the tire weighs according to that.
Okay, well, now that's, okay, I guess there is something there, isn't there?
Well, I just thought so the wider would be heavier.
Well, that's a valid point, I guess. If it's a wider tire, in that sense, it probably does, yeah. Assuming so I would buy that, that's fine. Assuming that the tires are equal in weight, or they're close enough to being equal in weight as to not be much of a difference, then it wouldn't really make any difference, yeah. Okay, but that's a good point. Does that make sense? Because that doesn't show up in the equation, right? Is that realistic? Well, to some degree, but is this a perfect model of friction? The answer is no, it is not. It's just a very convenient one to use. That's a pretty easy equation to apply, isn't it? It's not perfect though. I mean, there really are, it does a very good job of approximating what happens, but it's not perfect. But very little in physics is perfect, honestly. It's just all kind of a model to try to do the best we can to describe things. From the top of a tall building, here's the one. If you drop 2 table tennis balls, one filled with air and the other with water, both experience air resistance as they fall. Which ball reaches terminal velocity first? Do they hit the ground at the same time? Okay, so let's draw a free body diagram here, right? This will be helpful. So we've got, oh boy, we're out of time. That's okay, we get this one done. So we've got these 2 tennis balls. There's one tennis ball, and that's the one that's filled with sand. And here, or gravel, whatever it was. And here's the tennis ball that's just filled with air. Okay. What can you tell me about the forces acting on let's go action-reaction pairs. Okay. What's an action-reaction pair acting between the tennis balls and the earth?
The earth pushes, pulls down on it, that's supposed to.
Okay. Earth pulls down, tennis balls pull up, right? Okay, and with weight. Well, which of those tennis balls is going to weigh more? Okay, the one that's filled with, what was it, sand or water or gravel or something, I can't remember what it was. But this is the one, this is pulled down much more forcefully than this one is, right? Okay, so if the tennis balls are going to reach terminal velocity, what does that mean? What is terminal velocity? That's when the speed becomes constant, right? What balances the gravitational force, the weight? What do you think? Why would an object, well, let's take an example of an object that's pretty easy to witness. Tennis balls, I don't have any here, and they fall pretty fast, but there, it's at terminal velocity. How come? Oh, okay, air resistance, right? So there's air resistance pushing up on the ball, right? Does that make sense? If it's going to be traveling at constant velocity, which is what terminal velocity is, what does the magnitude of the air resistance have to be?
The same.
Has to be the same as the weight, right? Okay, so for the case where we have the tennis ball that's filled with stuff, it's gonna have to have a lot more air resistance than the empty tennis ball. Now, what's going to cause an object to have more air resistance? Surface area, sure. Let's do a mind experiment here. We're gonna do a thought experiment based on your own experience as a 3 to 5 year old taking a trip with your parents on a nice sunny day with the windows down. What did you notice about when your hand was out the window? It got pushed back. And when did it get pushed back? When it was more fun, it got pushed back harder. When? When it went faster, sure, okay, right? So the air resistance, so we've witnessed this, right? So air resistance is increased when the speed of an object increases, right? So what's the only way we can account for this extra air resistance? It's gotta be going a lot faster. So what must be true of its terminal velocity? Must be a lot higher, right? The thing had to go faster to generate that extra force needed to counteract the extra weight, right? So which one's gonna probably hit the ground sooner? Yeah, the solid, the tennis ball that's been filled up, not the hollow one, right? Make sense? In physics, fun, we can explain all this stuff. Well, we say we call our quits here.